RDF, RPF, RP, RP. What did the book call it?
I have questions actually.
Okay.
Oh, are you?
Go ahead.
Oh, okay, yeah. It was this question it asked in the homework. It basically asked to figure out if delta H is equal to, greater than, or less than delta U.
Okay.
And I don't understand how to figure out what to look for into figuring out in the reaction. It's a combustion reaction of 1 mole of 1 butanol. And from that, you just get.
Do they just want a qualitative answer, or do they want a quantitative answer?
I think it's qualitative.
If it's qualitative, then you put it into one of 6 scenarios. But it depends. If it's a combustion reaction, the combustion reaction would be exothermic or endothermic? Exothermic. So then you would put it into one of 3 scenarios. Do you have the 3 scenarios memorized? Who has the 3 scenarios memorized? You can just tell me. Grab a fresh pen. Think about the 3 scenarios that we talked about.
Okay, so that's the constant pressure. Delta U. It's like I don't know anything about that. I can just skip that.
There's probably a total of 6 scenarios.
Actually, I don't think it's qualitative, Dr. Chabal. It was quantitative. Because they talked about the change in moles.
Okay, if it's quantitative, then you have to do a calculation like the one we did in class.
It's number 64, chapter 7.
We did a calculation like that's similar in class. Take a look at that one first, and then we'll come back to this question afterwards. Did you catch that question we did? Was the combustion
Sucrose?
glucose?
I think that was for standard enthalpies of formation or something like that. Not for, this is relating delta H and delta U.
Okay. Well, okay. Take a look at the question. I don't know if you missed that one, but if you did, we can go through it. But do you guys remember that one we did in class with the delta H and the delta U, where we calculated the amount of work? Work is equal to minus P delta V. Okay, it would be the same type of problem as that. And so take a look back in your notes. If it's not in your notes, then we'll do it. But take a look first, because today, unless you guys, we could do another sample calculation like that, if you want. But let me talk about chapter 8 first, and then we'll do the sample calculation at the end about that, if you want to do that, or during lab tomorrow. But, there are 3 scenarios. Do you guys remember the 3 scenarios for exothermic? The 3 scenarios are delta U is greater than delta H, delta U is equal to delta H, delta U is less than. So there are 3 scenarios there. And how do you know which scenario it's going to be? You look under constant pressure conditions, does the volume change? And so maybe I need to do this now. You guys. are drawing a blank on this. You know, if you're drawing a blank on this, then are you going to be prepared for next week? No, unfortunately not. At least by this time, since we covered it so long ago, you know, if you're reviewing your notes, you would have probably seen it a bunch of times by now. And by this time, I was thinking it should be automatic, you know, 3 scenarios. What are the 3 scenarios? The 3 scenarios are when the volume, when the volume is constant at constant pressure, when the volume expands under constant pressure, and when the volume contracts. But do we even have to know the 3 scenarios? We don't have to know the 3 scenarios at all to do this problem. To do this problem, you just work through the math. Working through the math, what do they give you in this particular problem?
They just tell you the complete combustion of 1 mole of 1 butanol.
Okay, 1 butanol. One mole. Complete combustion of 1 mole of butanol, that's all they give you?
Yeah.
They need to...
Oh, they say assume that only significant change in volume during a reaction at constant pressure is that associated with changes in the amounts of gases.
Okay, that we don't need to know. Actually, they're just asking, is delta U equal to delta H? Or what is delta U, the relationship between delta U and delta H? This is qualitative. Unless they ask you, did they ask you to determine delta U or did they ask you to determine delta H?
It says determine
the relationship between the two, so we don't have to do any calculations for this, right? This being qualitative, we could just take a look and see. One thing we have to know is, what is butanol? Is butanol a solid, a liquid, or a gas? It's a liquid. How do I know that? Well, think ethanol. Is ethanol a solid, liquid, or gas? Is propanol a solid, liquid? It's a liquid. Ethanol is a liquid. Propanol is a liquid. Butanol should be expected to be a liquid. It's only when you get to these huge alcohols that they become solid. You know, very, very large alcohols are solid. But we expect butanol to be a liquid, and then we combust a mole of this. Okay, so we're going to form what? Carbon dioxide and water. Now, water, is it going to be a liquid, solid, or gas?
liquid.
It's got to be a liquid. And so we got gas here and gas here. Now, let's balance this. We need 1, 2, 3, 4. We need 4 CO2s. How many hydrogens do we have? 5, 7, 9, 10 hydrogens. So we need 5 waters. That gives us 1 oxygen here that's fixed. 8 plus 5 is 13 oxygens. So we need 6 O2s. And so this is a scenario. It's exothermic. And what's happening to the volume? The volume before versus the volume after reaction. Actually, how, you know, a mole of gas is about how many liters? That's at STP. 24.5 for 1 atmosphere, 24.7 or so for 1 bar. So let's just average it. We're going to just, or estimate it as 25 liters per mole. Have you heard me say that before? So 6 times 25 is 150. So we're going from about 150. What about this? We're talking milliliters here, right? And so if we got 150 liters and there's some milliliters in there, is it going to make that much difference? No. And so this is the assumption they're talking about. So we're going from 150 liters to 100 liters. And this is also milliliters of water. And so when we compare liters, hundreds of liters compared to milliliters, we can say that the milliliters are kind of negligible. Now, if we want to do an accurate calculation, we'd never do that. If we want to do an accurate calculation, then we'd incorporate the milliliters in there because that's a change in volume also. And so we would do that. But in order to do that, we need to know the density of water. Well, density of water is no problem because everybody should have that one memorized. But you'd also need to know the density of butanol. And so I did it two ways in class. I did it where we looked up the density, right, of the liquids and whatever else, solids. We looked up the densities and then we calculated those. And then we did it the other way where we kind of ignored. Remember that? I didn't finish the calculation where we ignored it. But you're going to have the, don't you think you're going to have the same scenarios pop up in an exam? And so if you want to be prepared for the exam, you got to think, okay, what are the possible scenarios? One, I'm going to make you calculate it. I'm going to make you calculate the volume of this liquid and add it to the volume of the gas. And you aren't going to estimate this, you're going to actually figure it out because I'm going to tell you the pressure. If I don't tell you the pressure, you're going to assume a pressure of what? 1 atmosphere. Or 1 bar, either. And so, you know, that's just standard. This is standard things you'd be thinking about. You know, and this is always helpful. Before the test, you go, well, we did this example problem in class. You know, what can I ask you for the test, which is next week? You know, what am I going to ask you on the exam? And so you think about the different scenarios. Will I make you calculate it? I could, because we did an example of that. Would I make you estimate it and make an assumption? We could, because we did an example of that too. And so I expect you to be comfortable either way, you know, making assumptions or doing the full calculation. Okay. But this one we don't need to do it because we're missing information. You know, this is why I asked you, was there anything else? Because the only way we can calculate is if we're given a delta U or a delta H or the delta H of formation of butanol. Is the delta H of formation of butanol in Appendix D? It probably is. So we could, you know, we could calculate it. If we have the delta H of formation of butanol in Appendix D, then what can we calculate? We can calculate the delta H of this reaction. And if we have the delta H, then we can calculate the delta U. Now, as far as the formulas go, you know, for like, the formulas for like Chapter 6 that give you those formulas. But the formulas for Chapter 7, it's a little bit different. The formulas for Chapter 7, you have to either derive them yourself or memorize them. And the reason is it's different. The formulas for Chapter 7 is I can't just give you the equation because the equation has restrictions on it, right? And so you got to know those restrictions. It's like if I gave you the van der Waals equation, there's no restrictions on that. You use the A, you use the B, you plug it in, right? Along with the other variables, and you do your calculation. But for thermo, as you'll find out, you know, there's some cases where delta H is not valid. Like all the time, people will do, let's say, bomb calorimetry and say this is the delta H, the heat of reaction. Is it? No. The thing, remember we talked about delta H and delta U, that one homework problem? How mixed up it was? If they didn't say heat of reaction, the heat of reaction, which of the following is true for the heat of reaction, if they just said the energy change in the reaction, then it would have probably made more sense. Their answer would have made more sense, you know. But and so there were certain restrictions on certain things. But one thing we know is we're going from about 150 liters, roughly, to roughly 100 liters. Now, are you guys okay with enthalpy diagrams? Are you guys okay with internal energy diagrams? Which one are you more comfortable with? Have you figured it out? Because all you need remember the internal energy diagram and the enthalpy diagram kind of tell you the same thing. So which one were you more comfortable with? Which one made more sense? Because maybe equally they make sense, maybe not. Maybe one is a lot easier to see. I'll tell you, we use enthalpy diagrams the most, but when you compare delta U and delta H, enthalpy diagram might not be the easiest because of, and I talked about this, because of the, and what did you say? I mean, you asked me, is it okay if you don't flip it, if you just add it your way or whatever, doing something like that, right? Well, it's the reason why I think enthalpy diagrams are more difficult is because of the minus the work, which is, which means that when you're thinking about losing energy means you drop down in energy. But when you're looking at an enthalpy diagram and the system's losing energy, it's going up, not going down. And it's because of the minus, right? And so I made mention of this, saying that the enthalpy diagram is a little bit trickier for most people because of the work. Right? What's easier for most people is the internal energy diagram. It's more easier to visualize this. Do you see why thermo is considered so hard? It's so hard because you got to keep track of so many things. But it's not hard. Thermo is not hard, actually, if you memorize all this stuff. If you memorize this from the very beginning, then it's not hard, at least at this level. So what are you more comfortable with? The enthalpy diagram or the internal energy diagram, or it's something that you just looked at once? It's something that you look at once. For me, the only way I could get this stuff is to look at it over and over and over again. And so, I was hoping by now you guys would have looked at it a bunch of times and figured it out for yourself. Of course I can sit here and tell you, what to do. Okay, do the enthalpy diagram. Ignore the internal energy diagram, right? But that's not going to happen all the time. So, is work done by the system or work? This work is done by the surroundings. So what does the work term look like? Does the system lose energy or gain energy? System gains energy. So delta, we're going to call this delta U because we're just going to look at a U. The system gains energy, and then it's exothermic, so energy is heat. This is under constant pressure, so Q is delta H. So which one's bigger, delta U or delta H? Delta H. Done. Done with this at the qualitative level. At the quantitative level, could we calculate it? Well, it sounds like they want us to calculate it. Why? Because I don't know. Do they want us to calculate? They just want us to tell which one's bigger? Okay. And so this is how you do it for this. Delta U and delta H don't come easily to anybody. I haven't met one person where it's come easily. It's just this constant drilling over and over that I notice that it'll start to click for people. But I'll tell you, I haven't met one person who said, oh yeah, that's intuitive, that's easy, got it. Not one person. This is why I spent so much time on chapter 7. Fell behind. Because I spent extra time this semester on chapter 7 than I usually do, because I thought, oh, I'll do more scenarios with that. But it's tough stuff, to get. And so go through the three scenarios for exothermic internal energy diagram. There's 3 scenarios, and drill those down. And then the endothermic ones, drill those down. If you're struggling for time, forget about the enthalpy, because I'll tell you the internal energy is easier. You should have noticed that, maybe. It should be more intuitive, because internal energy is just Q plus W. Before the test. Now, you're going to have to do more, obviously. You're going to have to be able to do the calculation. So try the calculation and see what you come up with. Okay. And try the calculation by looking up the density. Also this. Don't make the assumption. Do it without the assumption. Look up the density. Usually what you do is you do it without the assumption and then compare the value that you get to doing it with the assumption and see, did the assumption really increase the error in your calculation? So I got a question this morning, what's going to be on the test? What's going to be on the test is all of Chapter 7. Because that, even the calorimetry stuff is important for some of the latter ones, latter problems. So all of Chapter 7, Chapter 8, all of Chapter 8, and then Chapter 9 is going to go kind of quick. In fact, tomorrow what I'm going to do, because tomorrow's lab involves Chapter 10, 11 material. And so what I'm going to do tomorrow is I'm going to do some more catch-up, finish up Chapter 9, and then I was talking to some people who were having difficulty plotting the calorimetry experiment, graphs. And so if you haven't done those, if you've done those, great. Let me take a look at them and I'll see. I know a bunch of people finished them, but if you haven't done them, we can finish them up in the lab there, and then I'll announce a due date. I didn't really announce a solid due date because I wasn't sure how much access to Excel you have or graphing program you have outside the class. So it's, used to be very few people, but I was thinking everybody has access nowadays. So that's why I made you do it at home. But we'll do it. All right, so so I already spent this much time. Let's go ahead and finish this then. How am I going to get some numbers for this? Somebody tell me. How will I get the numbers? Okay, in other words, how many different ways can you determine delta U? Tell me all the ways you can determine delta U. This is, if I ask you a question like this, this is something I always think about. Should I just go ahead and tell you, or should you figure it out yourself? And so there's some things I want you to figure out yourself. One of the things is when you look through all the homework problems, you look through the lecture notes, you'll come up to the realization that delta U, what are all the ways you can determine delta U? How many ways did we determine delta U? Well, one way is by bomb calorimetry. That's one way. What's another way? And so you go through all the problems we did, and you go through all the homework problems, and you'll notice that the only other way to get delta U is from delta H. And so there's really only one way to get delta U, and that's from bomb calorimetry. What are all the ways of getting delta H?
Hess's law.
Hess's law. What's the easiest way of getting delta H? Not Hess's law, it's a variation of Hess's law called, and this I actually did mention, so A number of times I mentioned what is the easiest way of determining delta H. It's not coffee cup calorimetry. It's not Hess's law. It's first law of thermodynamics is usually used. Is this the first law of thermodynamics here?
Yes.
Yes. So I guess we could use it. The first law of thermodynamics would be range. Delta H is equal to delta U minus W. There's delta U. How do we get delta U? And do bomb calorimetry, right? So we're stuck. We're stuck because they didn't say anything about bomb calorimetry. That's what I was asking. Maybe they would. Do you see, the problem with thermodynamics is, all these branches, and all these connections take time and this is something I was studying because, it's happened to me. It's happened to me where, did I tell you about after I finished the final exams, I was shopping at Ralph's? Did I tell you about that?
Yes. And
then I finished the final, but I couldn't figure out one problem, and it was bugging me because, but it was too late because I already turned in the final exam. But there was one problem that was bothering me. And so like an hour or 2 hours later, I was standing in the line at Ralph's, and then click, all of a sudden, oh, so easy. Why didn't I think about that? Why didn't I think about that 2 hours earlier? I would have been able to do it. Get one extra problem done. And so I was thinking about that, and then I was reading some studies about, how your brain makes these connections. And, and it totally made sense because there were two ways I was studying. One way I was studying is I was doing very few problems and spending a lot of time on each one. Very few problems and spending a lot of time on each one. But, I felt totally lost. Even though, let's say I figured out that problem, I didn't know what the range of the problems were. I didn't know what kind of problem could hit me. I felt very uncomfortable, and I felt like I didn't really understand the material. And then I switched to doing all the problems, right? I tried to do all the problems, but not spend too much time on any particular one because I use the solutions guide. They say a lot of teachers, and in fact, a lot of my teachers said never use the solutions guide. Put your nose to the grindstone until you get it. And so that's what I did. I spent an hour, 2 hours on one problem, until either I gave up or I got it. After I did that, then I realized, boy, I know so much more. I feel much more comfortable with the material because, I feel more prepared for any kind of question that might get asked because I've seen the full range of questions they ask in the homework, and all the little variations. And all those little variations throw people off. As a teacher, I get this comment a lot. That is, the exam was nothing like the homework. The exam was nothing like what you covered in class. And let me tell you, when I was at UCSB, a lot of instructors used to joke about this because the exam was just like the homework. It was just like the stuff they covered in class, except what they did was they threw in an extra twist. And so that extra twist caused people to not even be able to associate that problem with anything they'd seen before, Well, anyway, to make a long story short, seeing that many problems, and doing it well ahead of the exam, I think what this does is it allows your neurons to make connections, to get it. And so what I think what just happened when I was at Ralph's was, the neurons made the connections just then, and then boom, it came, right? But before then, the connection wasn't made. And so the connections are made when you're doing this repetition. That's actually what I learned. And you don't have to agree with this or follow this, but I found it quite effective for me that, doing this in the repetition, like even before the exam, I wouldn't have seen the homework once. I would have seen the homework multiple times, because the first time it just doesn't stick. They said every single class I've said read the chapter 3 times. Biochemistry, they said read the chapter 5 times. Otherwise you're not going to get it. But I never had time for that. I think I told you this. I never, they said read the chapter once before and then 2 times after lecture, right? I never did that, especially since some of the books were 1,000 pages long. In 10 weeks, 1,000 pages is impossible, especially the pace I read. I'm not a speed reader. They say, some people say take speed reading, that'll boost your grade one higher. Some people say that. But well, anyway, what I did was I didn't go over the book over and over again. I went over my notes over and over again, and then eventually it stuck and made those connections. And the homework, many problems. And so then I get hit with this. Oh yeah, 3 scenarios, 6 scenarios. And I can figure it out which scenario it is. It's not, I think, for me, it wasn't about being like smart. It was just remembering stuff. That's all it was. In order to get an A in a lot of the courses, I didn't have to do any genius problems. I just had to recall information. In order to get that 90%, recall the information that was discussed in class. That was it. I didn't have to come up with some brilliant, new, novel idea. There was nothing of that. All right. I'll tell you, even, when I went to the PhD program, I was a little bit concerned because I thought, how could I come up with an original idea that nobody's ever thought of? And you know what I realized? Oh, it's so easy. Because there's so much stuff that people know very, very little of. And so you just pick something. But the only way you see that is because you've been reading a lot and you've been looking at a lot of stuff, and you see, oh, there's holes in this. There are weak points here. Somebody should do this experiment. Somebody should figure this out. And so PhD, even though a lot of people think, oh, it's hard to come up with an original idea, it's so easy to come up with an original idea because there's so much. The problem is how long will it take you to get any kind of useful data from that original idea? And some people's projects are just too hard that they stay in grad school for 10 plus years because none of their experiments are successful. Well, anyway, going back to this, what's the easiest way of determining delta H? If you've read this like 3 or 4 times, wow, it's so easy. What is it? Standard enthalpies of formation. Automatically, that's the first place I go. Standard enthalpies of formation. So delta H of this reaction is equal to 4 times the standard enthalpy of formation of CO2, 5 times the standard enthalpy of formation of H2O liquid, minus 1 times the standard enthalpy of formation of butanol. And what's the standard enthalpy of formation of O2? 0. And then do that calculation here. And we're done. We're done. We have Q. All we need is W. W is such an easy calculation, isn't it? W is equal to minus P V final minus V initial. If you want to qualitatively do it, V final is 100 liters, V initial is 150 liters. We changed about 50 liters, right? This is qualitative. If you want to do it quantitatively, we have 2 levels of quantitative. 1, we quantitatively figure out the volume of O2 gas based on the pressure and the temperature of CO2 gas and ignore the liquid. That's level 1. Or if you want to do it quantitative, level 2, then we would factor in this. We'd look up the density. We know we have 1 mole. How much does 1 mole weigh? Let's figure out the molar mass. We got that many grams. That many grams is how many milliliters according to the density. convert that to liters, add these two up, that's V initial. Water is easy. 5 moles of water, 5 times 18.02, that's how many grams, and that's how many milliliters. And so this is an easy calculation. That's V final. And we'll plug it in. Now, I'm not going to give you the conversion factor for this. Bar, let's say we do this in bar because we're using Appendix D, and this is going to be under standard conditions. Bar liters. I'm not going to give you that conversion factor, but it's an easy one to remember. Do you remember it? If you don't remember, the reason I'm not going to give it to you is because you should be able to derive it. We did the derivation in class. This is another thing that I noticed that people aren't doing. If you want to do better on the exams, there's so many things you could do to get better on, to do better on the exams. One, you got to make sure that you repeat the calculations we do in class at the bare minimum. Did it make sense to you? If you had that same calculation on a test, could you do it? You'd be surprised at how many people just watch. They just watch and learn. Well, I tell you, at UCSB, one of the professors, the theoretician there, he was telling me about his class. You know, I had to finish all my coursework by then, and so he's just telling me about this class he had of chemistry graduate students. And it's a quantum mechanics class. And so he was doing a calculation, and the calculation took 2 days to do. At the end of the calculation, he said, okay, does everybody get it? Are there any questions? You know, any problems? Let me know. And everybody said, oh yeah, it made sense. You know, it's easy. This class only had 5 students. And so, you know, 5 students, small class, made sense, right? And then he told me the next day he gave them a test. It was a surprise test, and it was a quiz. And he just said, okay, redo the calculation we just did, you know. And he was surprised because this is full of chemistry grad students who are very serious about it and who did well. But he said something like only 3 out of the 5 or something like that. 2 out of the 5. I think it was like only 2 out of the 5 could repeat that calculation. You know, they didn't do it. And so when we do a calculation in class, you should repeat it the same day. You know, you repeat it the same day, not repeat it right before the test. Maybe if he waited right before the test, then people would have done it. He shouldn't have given them a surprise, a quiz. Maybe warned them a little bit. But the point was that he made was that you don't learn by watching. You got to do it yourself. You know, so if you want to do better on the test, make sure you repeat all the calculations we do in class. Some people said, well, you know, the homework doesn't really relate to the test. Well, you know, sometimes it doesn't. You know, the homework is more broad spectrum. The test, I can't, you know, I'd like to test you on everything and put every type of problem in there, but I can't. You know, there's some types, otherwise it get too long. And so you got to expect that, you know. Yes, the homework is not going to look exactly like it because there are going to be some problems I can't test you on because it'd be too much. Like I was thinking, on the last test, I was thinking, can you imagine if I put a successive approximations problem on the last test? I mean, it would have taken another 3 hours, another hour, you know. It would have just been way too long. Eventually, I got to throw on a successive approximations, but the last test wasn't the one I was going to throw on. You know. But we'll see.
Is there going to be non-ideal gases on this test?
Yes.
So it's
Or was it? Okay, yeah, because remember we left off the non-ideal gases on the last exam, right? And so that is chapter 6. You're right. You're right. I didn't have it, but you're absolutely right. That could come up on. I have a chance. I could put that on this test, right? I could easily put it on this test. Are you prepared? Did you do that one? You know, I asked, I gave up asking, you know, because I gave problems. I give problems out and I ask sometimes, okay, what did you guys get? What did you guys get for the volume? Did you do it? Did anybody do it? You see, that's something you want to do. That's something that you want to start doing. In fact, I think that's more important than doing the homework. If you're running out of time, what do you want to do? Do you want to study the homework or do you want to study the problems we did in class? Which one do you think will get you more points?
Problems we did in class.
Problems we did in class. Some of the homework problems are a little out there, like MGH, 4 MGH. You think I'm going to ask you 4 MGH on the test? No, but on the homework it's fair because the homework can go beyond, you know, sometimes. Do you think I'm going to ask you 4 pi r cubed on any of our tests? No, but the homework there's problems where you have to use that, right? 2 pi r. You know, I don't care about the geometry stuff, but it's not to say homework's not important. You should do that too. Okay, but you know, I've been getting a lot of questions from a lot of different students about the test. You know, about how to improve exam performance, and what they should study, what they should do recently especially after that last test. And so these are some tips that you can try. If it doesn't work, you know, I believe me, I've tried everything that when I went to UCLA, you know, I tried everything. In fact, I should look for my biochemistry professor at UCLA. He had a little booklet of how to study biochemistry. I should find that and make a copy of it so you can see that if you want. It didn't work for me. Biochemistry is a lot of memorization. You got to memorize all the cycles. The only way I could do that is just by repetition. All right, so anyway, after going through that, tell me how to figure out the conversion factor between liters, bar, and joules. I don't want the calculation, just tell me what to do. How do I convert a liter bar to a joule? Or how do I convert a liter atmosphere to a joule?
Bars to atmospheres. Atmosphere liters.
Let's say I forgot the conversion factor. I need to derive it. Tell me how to derive it. Okay, there you go. Do you see? It's just recall. Could you recall? We did that calculation on the board. Can you recall it? This is just recall. It's not coming up with any kind of genius idea. It's just, can you recall the information? The only way you can recall it is if you have a photographic memory or by drilling it into your... It's not even drilling, it's just reading it. If you read it like 5, 6 times, it becomes boring. You know, you've read it the 7th time, you go, yawn. It's too boring because I've seen it over and over. It's like watching a rerun over and over again. You know everything that's going to happen. You know, I have friends that they know all the dialogue in the movies and all they do is repeat it, you know, because they watch the movie like 50 times. Well, you can do the same thing. You watch the movie 10 times, you already know it. Oh, it's easy. What do you do? Well, that's good. You still have more than a week. You can learn a lot in more than a week. I had friends that said, oh, you know, give up studying right before the test. I never gave up studying. But I never stressed out about it either. I just, you know, just flipping through the notes. It doesn't hurt to go through it one more time. You know? Flipping through the homework. You know, but that was like, I don't know how many times I've already done that. But right before the exam, you know, doesn't help. One time I did this. you know, well, forget it. I think maybe that's enough. But me telling you to do what to do, you know, you don't have to do any of this. You know, whatever you find that works effectively is what you should stick with. But if it's not working effectively, then try something new. You know, if you're not doing as well as you'd like to, which was the case for me, then try something different. And that's what I did. I kept trying and trying until I found something that clicked. And so if you're still searching for that something that's going to increase your performance, then do that. The book calls it an RPD. What does an RPD stand for? Radial probability distribution. These are like on page, I forgot what page these are in your book. And which one did we look at so far? Did we write or I just showed it on, huh? Okay, which one did we look at? Hydrogen, 1s? Well, anyway, it looks like this. This is 1s, or psi 100. So 1s, RPD. And so this is the distance out from the nucleus. And so what does the peak tell us? The peak tells us the most probable distance. Did we compare the 2s and the 2p? No? If we look at the 2s looks something like this. Two-S has a node here, which is a node. And the peak's out here, which tells us the most probable distance is here. That's the 2s. If we compare this to the 2p, the most probable distance is the 2p. A little closer. 2p. And so what this means is that the electron and the proton, or the protons, in other words, the electron and the nucleus are naturally attracted to each other. And so there's this natural attraction in which the electrons are going to be pulled into the nucleus. Therefore, to pull the electrons further out from the nucleus is going to require work. In other words, to pull the electron further from the nucleus is going to destabilize the electron and make it higher in energy. And so when I look at this, it looks to me like the 2p electron is closer to the nucleus based on its most probable distance than the 2s electron. Therefore, I would expect the 2p electron to be lower in energy than the 2s electron, just based on its proximity to the nucleus. Right? We already talked, did we talk about this? 53 picometers, we talked about that? But do you know that both of these orbitals have the same effective distance? Both orbitals have the same effective distance from the nucleus. In other words, the electron in both the orbitals have the same effective distance. And so how can that be? Because it looks like the 2p is closer than the 2s. The reason is because the three-dimensional distribution of the orbital around the nucleus. When I look at a 2s orbital, the 2s orbital is spherical. This. So I got a 2s orbital. There's some node in here. Don't worry too much about. But if you were standing on the nucleus, and looked out in any direction, you would see the same thing, right? You'd see the same electron cloud. So when we look at the electron cloud, it's the same in all three dimensions. So we got electron cloud here, the node, and then the electron cloud out here. Wait a minute. The electron cloud is more dense near the nucleus. No, it's thicker near the nucleus. This is a 2s orbital. The electron cloud is thicker near the nucleus. Why is the peak far from the nucleus? The peak is out here on the other side of the node. Why is that? Yeah, it has to do with remember the volume of the rings around here? And so actually it turns out a ring here, even though the dots aren't that dense, this ring has such a large area in the context of this board that it captures a lot of dots. So. All right, so we got something like this for the 2s orbital. When you're standing on the nucleus, anywhere on the nucleus, and you look out, it's all the same. You see the same cloud, right? What that's called is, that's called isotropic. Isotropic means the same in any direction, the same. Whereas a 2p orbital is not isotropic. It depends on which direction you look at. And so if we look at a 2p orbital is going to look like this. So here's my 2p orbital. And the 2p orbital is going to have a lot of dots here. Remember the highest density is right off the nucleus here, and then it's going to drop off. Same thing here. The highest density is going to be around here, and then drop off here. This is not called isotropic because if you're standing on the nucleus, it depends on which direction you look. If I'm looking out in this direction, do I see any 2p electrons? None. And then if I turn and look at this direction, then I see a lot of electron density. So there's a much higher probability I'm going to see that. And so this is called, not isotropic, do you know what it's called? These aren't in your book, and I'm not going to test you on them, but these are very common words in science. Talk about it now. It's called anisotropic. And so isotropic just means the same in 3 dimensions. Anisotropic means it's different. And so what we have to do is this. In order to make a fair comparison, we either have to bunch up the 2s electrons in a cloud like this and a cloud like that, right? We have to even the playing field. We can't compare something that's isotropic with something that's anisotropic in terms of electron, nuclear interaction. It just doesn't make sense, right? And so when I look at the most probable distance, the most probable distance for the 2p is closer than the most probable distance for the 2s. But is that a fair comparison? No, it's totally unfair because the 2p, even though it's closer, the volume of interaction is smaller. And so what I have to do is I have to imagine spreading the 2p electron cloud out over 3 dimensions. In other words, I got to normalize things. Normalize means even the playing field. So if I normalize this, then I'll find that spreading the 2p out over 3 dimensions to make it isotropic means that the density isn't going to be as concentrated here. The density is going to spread out, and then the effective distance is going to be the same. Does that make sense?
So you said spread out, you would normalize the 2p by spreading it out, but it's not going to be as dense, it's not going to be...
Well, if you spread out all the dots, then is it going to be as dense here? No, the density is going to decrease, and in fact, that's going to pull out the most probable distance. In other words, here, yes, this is going to have a stronger interaction with the nucleus here and here, but we got to average it. Zero interaction, strong interaction. And so this is like 0 plus 2 plus 0 plus 2 gives me 4, right? Versus plus 1 plus 1 plus 1 plus 1 gives me 4. So when we normalize it over 4 quadrants, let's say, then it comes out the same. And so this is why both of these orbitals, even though they have different peak in the RDF, are actually the same distance. Now, if the electron's the same effective distance, what does that mean for the energy? That means the energy is the same, because, you know, if it gets closer, it goes lower in energy. If it gets further, it goes higher in energy. And so that means the 2s and the 2p, even though they're totally different shapes, will have the exact same energy. And so this was to answer what question? The question was, why? This is the 1, 0, 0, the 2, 0, 0, 2, 1, 1, 2, 1, 0, 2, 1, negative 1. These are the 2p, these are the 2s, this is 1s. Why is the 2s and the 2p the same energy, even though they're totally different shapes? Remember, these are energetically degenerate. This is for the hydrogen atom. And then the same thing happens. Did I already talk about this, or I haven't talked about this yet? So I'm out of sync with the afternoon class. I just want to make sure. I mean, with morning class. Sorry. I just want to make sure. Now I'm actually behind in the afternoon, but ahead in the morning. Actually, I've got to be consistent. I did -1, 0, 1. So -1, 0, 1. All right. Three, 2, 2, -2, 3, 2, -1, 3, 2, 0, 3, 2, 1, 3, 2, 2. This is 3D. This is 3P. This is 3S. And so even though the shapes are totally different, they both have the same effective distance, therefore they have the same energy. What about the 3? The n equals 3. The 3p orbitals are like this dumbbell shape. The 3d orbitals are like cloverleaf shape. They're totally different, right? The shape. But they're going to have the same energy because the effective distance is the same. And so we know that. Yeah. And this goes on, you know, so we'll have the 4, the 5. We did the 5, right? All the way up to, what's the highest? Infinity. All right, so in certain ways, did I draw the transitions there, the red? Did we do that? The red, the green, the blue? The red line is when we have an orbital and the n equals 3 and it drops to the n equals 2. Did we do that? Yeah, okay. And so the interpretation is totally different. What Bohr said that we have the first orbit, the second orbit, the third orbit. But in quantum mechanics, we don't say that. We have the first orbital, And then we have a bunch of orbitals, 4 orbitals in the second level, and the electron can be in any of these orbitals here. They're all the same energy. And if it's in one of these orbitals and drops down here, actually from 2 to 1 is UV. It's a big energy gap. From 3 to 2 is a smaller energy gap, and that turns out to be red. But it can occupy one of these here. And so it's not orbiting around the nucleus. It's in an orbital. In an orbital, you know the energy and the shape, the probability distribution shape.
Is it correct to call those subshells, or are they?
Remember we had the rule or the law of subshells? And so here, n equals 3, we had 3 subshells, the 3s, the 3p, and the 3d. And in the 3d subshell, there are 5 orbitals. In the 3p subshell, there are 3 orbitals. In the 3s subshell, there's 1 orbital. Okay. The number of orbitals in the subshell, we came up with the law of the number of orbitals in the subshell. What was it? 2L plus 1. So what we did at this point is we try to apply this to other 1-electron species. Hydrogen and other 1-electron species. Okay. Let's see. If I have another 1-electron species like He+, helium plus, what's the difference between helium plus and hydrogen? Well, both of them have 1 electron, so that's the same. What's the difference is the number of protons. And since there are different isotopes of helium and different isotopes of hydrogen, I'm going to ignore the neutrons. And so helium has 2 protons, hydrogen has 1 proton. And so what is that going to change? You tell me, what would having 2 protons instead of 1 proton in the nucleus change in the orbital, in the RPD? How would that change it? We'll give you a minute to think about it.
Told you how to do it, so you don't do the homework, you just, and you do the homework, and you just use the solution and don't spend too long, you just want it in your brain, and then redo it like a couple days later, before the test, and rewrite your notes, go through it. It's not
The last test, there was enough information, so it's like,
well, no, I know, I'm not saying like totally ignore the homework, but you know which ones you probably not gonna know. That's what
like the instant.
yeah, but no counterintuitive stuff, he's definitely gonna put it up, and he did, so yeah.
We're gonna have more caliber.
Yeah, he just said it.
I don't know, that's what I was saying, maybe we made a mistake.
We have to use chapter 6, the non-real, non-ideal, or non-real, and then we have to do everything from chapter 7, including their rules, including the stuff you already covered. You only have 1 class.
I don't know. That's the one of my so what helped me a lot is when those questions we do in the last minute. Those that filled in the gaps for me.
Uh-oh. Do you read the book at all?
I do.
How many notes?
I read per paragraph, like, or sections, like
Have you spent those?
No, how many times do you want to
I
say
don't do it that way. I read like
a short section
and if I don't understand, I just reading it until I understand. And I don't move forward like.
well, your rating is not working here.
Yeah, I would
Just said, you
Dr.
just said.
Chabot, I take things like this, like I take notes in the whole book.
I'm sorry?
I take notes in the book like this, but like,
Okay.
do you think like it's just best to study the book for the theories and like your
Well-
lectures for calculations?
No, let me tell you what I did. What I did was, because I'm not, they said, one, speed reading helps, and number two, shorthand helps. So I'm not a speed reader, and I don't know how to do shorthand.
What's shorthand?
Shorthand is like, court reporters, like they can record the whole transcript of the court dialogue. And in order to do that, either you gotta type at an insane pace, or shorthand. Well, they know shorthand. And so the people who know shorthand can, if somebody's talking, they can record every word that they're saying, no matter how fast they're talking. And, that would have, I think, would have been a big help, but at the time I didn't take any shorthand, I didn't take any speed reading. And those were things that were pushed, if you want to do good in your class. So what I did instead is this. I'm a very slow writer. And so when I go to, this happens at conferences too. When you go to a scientific conference, they just talk, and they talk fast. And I had a lot of classes like history of French film. I took history of French film. She talked so fast. I could write maybe 10% of what she said, 20% of what she said. History of French film, though, I was lucky because she allowed everybody to record her lectures, so I just recorded it. And I tried something else. I tried because I was reading about subconscious and all this stuff. So I tried to put on my headphones. The exam was the next day, so I put on my headphones and just went to sleep, thinking that maybe that will go into my subconscious and register. This is how out there I was because, I was trying everything, right, to improve my grades. The weird thing was, I think it worked because on the test, it's just essay questions. She asked an essay question that she spent 20 minutes in class talking about. Normally I can't write that down, but I heard it, and so I remembered that. And all I did was write what she read. What she said. I wrote what she said, and then she wrote a little comment on my paper. And so I thought, wow, that was some easy points. But so what I did was this. I tried not to have a class back to back. Whenever I could, I made a gap between my classes. And it's easier at UCLA because they offer so many sections, right? And so if I had an hour between classes, that was perfect because that would give me enough time to go. There's a place called Kirchhoff Coffee House at UCLA, which I went to all the time. It was just really noisy because I like really noisy places because it's white noise. There's another place I used to study, which is at the bottom of Powell Library. So you go in the basement there, there's like a dungeon, and it's really quiet. But, it echoes. Every little sound in there echoes. And it's like being in an isolation chamber. There's no noise, and it's hard, I think it's like torture. They have a torture where they isolate you from sensory information, right? So I went to Kirchhoff Coffee Shop, and then what I did was I read my notes. And the thing is, I couldn't write it, but I could remember it. I could remember it, but it was a short time window that I could remember. And so whatever I could remember, I started writing quickly and filling in as many gaps as I could. And so there are huge gaps, and I left gaps there. I left lots of space so I could fill in gaps because I didn't understand it. I didn't write it all down. But when I got to the coffee shop, I'd start writing everything down and then fill it. And so after I did that, then I said, okay, which places still don't make sense? And which places still didn't make sense? Then I cracked open the book and started reading the book. The thing is, it's focused reading. So I would only read the sections because a 1,000-page book, you can't read the whole book. It's impossible. Because even the Chem book, the Chem book is like 10 pages in an hour if you're lucky, you know, because you got to do all the calculations, all the sample problems, right? I think I timed my pace in Chem. It's like 5 pages an hour or something like that, 6 pages an hour. But the thing is, I would read those sections, which I felt shaky on, and then if it made sense, then I'd write in my notes, you know, well, this is what this meant. This is what that meant. This is how you do this. And so I'd be writing myself little explanatory notes. This is what's going on, you know. This is what he's talking about, she's talking about here. Okay, but sometimes the book, I'd read the book and I go, gosh, this still doesn't make sense. You know what I do? If the book still didn't make sense after reading that section 3 times, I grabbed another book. You know, at the library they had a whole bunch of books, General Chem, whatever else. I grabbed more books and then read those sections in different books. The same section in different books is presented totally different. And so, for example, in Petrucci, it might be totally confusing, but in a different book like Tro, it might click, you know? Or I went back to the intro book and read the intro book and then read our book, you know? And so I used lots of different sources. If those didn't work, you know, if I couldn't get it from our book and I couldn't get it from any other books I had, and we have lots of books in the room across the hallway, there should be a whole bunch of other books there on from different authors for General Chem. If that still didn't work, I went to the office hour, you know, and then I asked because it's still confusing. I read the book, I read through the notes, went through all this, went through the homework. I couldn't figure it out. And so I went to the office hour and then got it explained to me and then figured it out. And so by the time the exam came, then I felt prepared well before the exam. I never did before. Before I started doing this, I was doing all-nighters all the time. After I started doing this, I stopped doing all-nighters. I didn't do any all-nighters after I stopped doing this. I did lots of all-nighters before that because I didn't have to cram. I mean, I've been going through this, and by the time the final exam came, you know, finals week is like total high stress. You know, at UCLA, they only have finals. Here, it's even worse because not only do you have finals, you have classes too, and they're still lecturing. And so UCLA's got it better than you guys have it here. But by the time finals came around, you know, I didn't really have to study that much for the final because I'd already gone through it so many times. You know, it was like an old a rerun, getting tired of it, you know, kind of thing. I mean, there's always new stuff to learn. That's why I never gave up. I kept going through it because I was thinking, what kinds of questions, what kinds of twists could they ask? What kinds of twists they could ask? That's why I went through the homework, every single problem. Who told me about doing every single problem in the homework? Do you know who told me this? Pre-med, you know, pre-med friend of mine did this, you know, and he was doing very well, and I was asking him. But he was doing all the problems, not just the ones that were assigned. And, you know, his dream was to go to medical school from a very young age, like 5 years old or something. He already decided he wanted to become a doctor. He was going to do anything it took. And he always wanted to get the top class, the top score, the top grade in the class. Whereas for me, I boiled it down to this. You know, of course, I'd love to learn everything. But you got to be somewhat practical about this. You know, I just felt that, okay, I need to learn enough to get a 90%. You know, I want an A in the class, but I don't need to learn to be the very top, unless, you know, it's something that interests me, you know. And so there are some classes I push to be, you know, I try to be the top. But a lot of the other classes, just the 90 is okay. And just a 90, I figured I could get by just reading the notes. So I figured. Well, anyway, that, you know, for me, it was a shock because I was at Santa Barbara City College originally. And when I was at Santa Barbara City College, I was on the dean's list, you know. semester after semester. Dean's list is you just have to get over something, 3 point something. I forgot what it was. And so, you know, when I went to UCLA, I wasn't really expecting much change. I was thinking, okay, I'm on the Dean's list here. I should be able to get on the Dean's list there, right? But no, not only did I not get on the Dean's list, I was worried about I was worried about passing the course. You know, to go from Dean's list to being worried about passing the course. The first course I took at UCLA, thermodynamics. Do you think I knew what delta H was? This is the first quarter, UCLA thermodynamics. I didn't even know what delta H was. I knew how to do all the calculations. You know, delta H calculations were easy. But the problem is, you know, if I do a delta H calculation and it's not valid, then it's the wrong answer. This is like, okay, I'm going to use the ideal gas law I'm going to use that. The ideal gas law is easy. I know how to do it. But I'm going to use it for gas where it doesn't apply. The gas is so non-ideal, you'd be wasting your time calculating it using the ideal gas law. I was at the point where I didn't know, you know. I knew how to do ideal gas law, but I didn't know where it was valid. Or I knew how to do delta H, but I didn't know delta H was not valid under conditions like the bomb. You know, I thought, oh, the bomb's going to give me the delta H, you know. But it didn't. The bomb gives you delta U. And so I went from being on the Dean's list to the first exam I took in thermo, D. I got a D. The problem is there's only one midterm and one final. And so now I'm really in bad shape. I needed to. And so this is why I spent so much time thinking about studying. Whereas the guy next to me, A, top score. The guy next to me is the pre-med guy. The guy next to me did every single homework in the thermal book. Whereas I'm doing one problem, I'm spending 1 hour on one problem in thermo. And where am I getting? I'm still not getting it. You know? I do 4 problems total. Before the test, I do maybe, I don't know, there weren't that many problems in the homework. But, you know, I didn't see it. You see little blips here, little blips there, but you don't see the whole picture. It's like looking through, you know, what is it? It's like trying to see the scenery through, you know, louvers. You know, you don't see, you just see through the cracks, right? And so you see certain parts, but you don't see the whole picture. And so this is why I thought, you know, what he's doing is the way to do it. And so after that, then I started doing, because UCLA was nice. At Santa Barbara City College, they never gave us the complete solutions guide. They only gave us the selected solutions guide, the odd problems, whatever. But UCLA, every class I took there was a complete solutions guide. They figured, complete solutions guide, no problem, because we're going to ask you questions that are going to be like this, you know, that are going to be different than this. And so, anyway, that was my experience there. So what I did, and I did lots of different things, but that's, you know, I managed to pull out of that nosedive in thermo, but it was a big wake-up call because I got a D, or maybe it was an F. It might have been an F on the first test, and then I pulled off a C in thermodynamics, and I felt fortunate because a lot of people failed thermo. In fact, did I tell you about the bumper stickers? And so, but you know, I wasn't happy with a C in thermo at all. Fortunately, I didn't. You know, when I was at Santa Barbara City College, you know, I didn't really care too much until I decided to transfer. Like in calculus, the first time I did calculus, I didn't do any homework. I didn't study. I didn't do anything, and I ended up with an F in the class. Yeah. And then I thought, oh my God. I wasn't expecting an F because I never really had to study that much in high school or anything like that, right? And then And then I studied. So the next semester I repeated calculus, and unfortunately I got an A. It was just the first semester of calculus, so it wasn't that. Calculus can be very tough depending on what they cover. So I was lucky for that. But I made it a point because I thought, okay, I got an F. I got to try harder. And then when I went to UCLA, it was a wake-up call. And so after that C, then I had to figure out how am I going to get back on the dean's list. And then finally, after that first 2 quarters or so, then first 2 or 3 quarters maybe, then I was on the dean's list after that. So I was consistently on the dean's list after a certain point. But that was my goal. I wanted to get back on the dean's list. So therefore I had that tweak the way I did it, 90%, for most classes. And then the classes I was really into, what I wanted to do very well on. But the classes, when you transfer to a school like UCLA, what I think one of the best ways to learn like what your major field is by doing research in the field. And so I didn't really, since I'm burning a lot of time here, I didn't really feel like I was learning anything, to be honest, taking classes. I didn't really feel I was learning, because remember I told you that I was thinking a PhD, how can you come up with an original idea to have it as your PhD dissertation? It wasn't until I started doing undergraduate research at UCLA, and they made it easy there because they have a student research program and they have all these other things. It wasn't until I started doing undergraduate research that I saw where is the cutting edge of the field. Reading in the book, the book information is kind of behind, but when you're working in the lab, you see where the cutting edge is, the people who are working at the cutting edge, and what it takes to be at the cutting edge. Well, what it takes to, all of you can be at the cutting edge of science, because there's so many unanswered questions, so many things that people want to know more about. Simple things like, for example, Ebola, transmission of Ebola. There's an original research idea, right? Lots of people are working on it. But can it be transmitted through aerosols? Can it be transmitted through air? That kind of stuff, right? And so in chemistry, it's the same thing. When you start working in research, you start going, wow, there's so much that's not known. So much that's not really well understood. Somebody asked me, okay, what's the, how do certain drugs work, like antibiotics? Right now, there's a big push because they're really afraid that they're not going to have any effective antibiotics in the near future, because they say the bugs are outsmarting the antibiotics. That is, they're mutating, they're able to withstand those. And so, that type of stuff you see a lot of. And if you're interested, this is a plug for the chemistry club. And you don't have to be a chemist to do that, but if you join the chemistry club, you get a magazine like this, C&E News. And C&E News keeps you abreast of all the developments in the field, a lot of these developments. And you read these articles, and remember what I said a conclusion is? A conclusion is not a summary of what you've just written in science. A conclusion is, where do you see this field going? Where would you take it? What do you recommend other people do? And so when you read these and you get to the end part, it's usually, okay, these are still these unanswered questions that need to be tackled. These are the problems that need to be solved. And then it becomes easier to do. But to get there, you want to do well in your classes. So I would recommend, you have the videos too, so you can always make sure that your notes are complete and compare it with other people. But I would recommend before the next test, maybe starting today, start reviewing everything from non-ideal gases on. And so you review that every day. Like today, you review what you have in your notes. When you review your notes, I'm sure there's going to be gaps or things that you don't understand. And so between now and the test, make sure you fill in all the gaps and make sure you understand everything that was covered before the test. And that way, you should have some confidence going into the next test. Okay. But the nice thing is we still have time. So if you review your notes today, then tomorrow you can ask me questions like this delta U, delta H stuff. But you know, to discuss the delta U, delta H stuff, I want you to make sure you looked at the problem we did in class, you know, to see what you're getting stuck with, and to see the kinds of variety you might see. Okay. So do that before exam 3, and then you know, we'll set aside some time in class. We can cover this, you know, answer your questions. You don't have to, or you can come to the office hour if you want to, and we can cover it then. Okay. Tomorrow I'm going to do some more catch up.